All right. So, but we are actually interested in quantum mechanics. What we did above is, of course, very interesting, and I will come back to it. In quantum mechanics, we are, in general, interested in the L goes to infinity limit, right? Now, in the L goes to infinity limit, what happens is that phi of x gets replaced by psi of x, which is, excuse the noise, which is an L squared integrable function, right? So, and I'm very sorry, there's work being done around. Okay. So what is psi of x? Psi of x looks like 1 over square root of 2 pi. Forget about the factor. We are still in mathematics land, so there's no h bar or time yet. I will come back to that. So a of k e to the power I kx d of k. So what we want to do is we want to be able to invert this function. So if I give you an L2 integrable function, ak, you want to be able to find, so psi of x, you will want to, in general, you want a recipe for finding ak. Okay? So anyway, we have done this in practice for a particular psi of x and ak. We just did this earlier today. But what I'm interested here is, what kind of formal machinery we can introduce analogous to the Fourier series that we just saw. Okay, so the way to invert this is to multiply both sides by square root of 2 pi. So on the left-hand side, we get 1 over square root of 2 pi. On the right-hand side, I have 1 over 2 pi. And multiply both sides by e to the power minus I k prime x. So if I do that on the right-hand side has an integral already with respect to k. But now I am multiplying e to the power I kx by e to the power minus I k prime of x. Okay? And then I integrate both sides with respect to x from minus infinity to plus infinity. Okay? So this is what I want to do. Now, remember that we have defined a of k to be 1 over square root of 2 pi, the integral of minus infinity to plus infinity, psi of x e to the power minus I k prime x d of x, which is exactly the left-hand side, right? So the left-hand side is just ak. So the right-hand side must also be, so ak prime. So the right-hand side must also be ak prime. So in other words, if I write the left-hand side now as the right-hand side, right-hand side as the left-hand side, I'm just rearranging it. I'm taking the 1 over square root of 1 over 2 pi inside the bracket, and the integral over the x eik minus k prime of x of d of x, and then d of k, this is equal to a of k prime, right? This is the requirement. This is my consistency. So this means that there must exist a function defined in the following way. So this function, we define it to be delta k minus k prime. In other words, delta k minus k prime is 1 over 2 pi integral of going from minus infinity to plus infinity e to the power I k minus k prime times x, so not by x, d of x. Now, this function is defined in such a way that if I integrate over k multiplying ak to delta k minus k prime, the delta function picks out one particular value of one particular value of a, which is the value of a when its argument is k prime. Okay, and this is the defining property of the delta function, and this delta function is called the Dirac delta function. Okay. Although I define the Dirac delta function through this expression, this is actually just a formal expression for the Dirac delta function. The defining definition, the definition of the Dirac delta function is actually this relationship. Okay. So, do you follow?
Yes, sir. So
okay.
A of k needs to be a well-defined function in this case?
Exactly. Yeah, A of k needs to be a well-defined function. Yeah. Okay. So let me make some comments. And comment number one is that, as I said, it's the equation 1 over 2 pi minus infinity to plus infinity e to the power I k minus k prime x d of x equals 2 delta k minus k prime. This is a generalization. Of the inner product en equal to delta mn for the Fourier series. Okay. For the Fourier integral. So the difference is that for the Fourier series, the labels for my basis functions were discrete, but for the Fourier integral, the labels for my basis functions are continuous. And the right-hand side, the Kronecker delta had a discrete index structure. Here, it's a continuous index structure. So I can think of psi of k, function of x, to be 1 over square root of 2 pi e to the power I kx as basis functions for an infinite dimensional vector space. Okay? So, yeah?
But this time it should be uncountably infinite.
Exactly. Uncountably. I'm not sure if that makes sense grammatically, but yeah, this is not an English class. So what we are saying is that psi of k comma psi of k prime is defined to be integral from minus infinity to plus infinity of psi of k star of x, psi of k prime of x, d of x, and this is given by delta k minus k prime. Okay. So this is the function, the L2 generalization of this relationship. So I hope my hope in dwelling on this is to kind of nudge you in the direction of thinking about functions, L2 integrable functions, as a space of vectors, infinite dimensional vectors. There are a lot of subtleties, such as convergence, because this is kind of a singular expression, as we shall see. So there are lots of mathematical subtleties that we don't have for finite dimensional vector spaces. But there's a lot of beautiful mathematical structure, and quantum mechanics takes full advantage of that. Okay, and Dirac was one of the first people. I think he was the first person to recognize the rich linear algebraic structure behind quantum mechanics, which inspired Johnny von Neumann to put quantum mechanics on a more firm mathematical footing. So I'm actually going to finish today's class on time because I have an important meeting afterwards. So there are about 10 minutes more time. So let me just give you a few more comments. And the second comment is something I've said before, the defining property of the delta function is, if you have a function, a well-defined function, say psi of x, and you integrate it over all of x, then you just pick out the value of that function at one value of the argument determined by the argument of the delta function. Okay. So this is the defining property. So we say that delta function samples the value of psi of x at x equals to x prime. So if I can rewrite this expression as psi of x, delta of x, in this case x prime is 0. D of x, then I should get psi of 0. Okay. Just 1 second. All right. Any questions so far?
No, sir.
So, if I take psi of x to be just 1, so this was comment number 2, then we see that delta of x minus x prime, going from minus infinity to plus infinity, d of x is just 1. Okay? So the area under the curve of the delta function, I should put it in quotes, of the delta function is 1. But it also samples the value of a function at a single point, which means that it is a weird kind of function. It has to be some kind of a very singular function, because if the Dirac delta function was not a singular function, suppose it was something like a Gaussian, and the area under the curve was 1, if I multiplied with another function, say something like this, it won't give me the value of the function at a single point. It would give me some weighted average of this function in that area, right? Which may not be this value. So this means that the delta function needs to be a kind of very singular function, okay? So the last comment is that the Dirac delta function is not really a function but a distribution. It's dealt with in the theory of distributions or generalized functions. And I think I'm going to end here and talk about representation of the delta function in the next class, as well as some application of the delta function. Okay, so when we formulate quantum mechanics more in mathematically rigorous terms in the coming weeks, the delta function is going to play an important and central role. Okay.